Well, we've already spent a lot of time in this class talking about conservation of momentum, conservation of energy, and we've been able to solve a lot of problems without specifically looking at forces in the way that Newton's laws are talking about. So why are Newton's laws useful? Well, let's remember that if we have something, say a block that's sliding across the floor, so that block is made up of a collection of atoms. And the floor is also made up of a collection of atoms. And not only that, but there's also, if let's say that this block is moving to the right, there's also air molecules that it's going to be bumping into. And so we have all sort, we just have an uncountably large number of interactions going on all at the same time, right? But what Newton's laws tells us, because we can just add the forces together, this allows us to make a much simpler picture of what's happening, because now we can just say, well, we can look at all of the forces that were due to the interaction between the block and the floor, and as we'll see shortly, we can call that the frictional force. We can look at all of the interactions between the block and the air. We can call that a drag force. And now we have a much simpler picture to look at. So in this case, our net force is just equal to, minus the frictional force, minus the drag force, the magnitude of those in the x-hat direction. And that's much simpler than having to look at all of the individual interactions that are actually happening. So again, we mentioned this briefly when we talked about conservation of momentum. But now in this section, we're going to really look at how we can take a look at a large number of interactions, and in this, for now, we're just going to set up how we would start a problem, and then the rest of this book is going to be actually solving problems and finding out what the motion of an object is based on the forces acting on it.